All right, so let's get started. And I am going to take 50 minutes, I promise. Hold you to it. All right, so of course we're going to be talking about query and index tuning. For those of you who didn't know, my name's Keith Murphy. I'm the DBA here at iContact. I'm also the editor of MySQL Magazine. I wanted to point that out. It is available at my website at paragon-cs.com/mag, and that is up there on our page. My email is up there, and my blog is up there also. Okay? So, the rules are, you can ask a question after any slide. That's the only rule. Okay? So, I have no problem with that. Don't do me one favor, don't interrupt me in the middle of the slide. You'll kind of figure out when I get done. Okay? And of course, we got to get the legal stuff out of the way. The views and opinions that are expressed by me are mine and mine alone, and they are not necessarily the views and opinions of iContact. Okay? What are we going to talk about tonight? We're going to talk about a few things. We're going to give you a quick overview of the server and how queries go through that server. Okay? We're going to talk about the slow query log. We're going to talk about the explain statement. We're going to talk about some things that you should avoid when you're writing a query. We're going to talk about indexing strategies. We're going to talk about the optimizer itself. Okay? We're going to talk about some schema guidelines, the query cache, and benchmarking. So, fasten your seatbelts because I'm going to have to go a little fast. I have about 50 slides. So you do the math. We've got about a minute a slide. So this is our overview of the SQL Server itself. Now, when you start a query, it's going to start up here in the upper left corner where it says Clients. That is your connection to the SQL Server. All right? That would come through like the MySQL client program or through your API of whatever language it is that you're using. Now, what you're going to do is going to get routed through the connection and handling part of the MySQL server, and it's going to analyze it. It's going to check the query cache first. Okay? If it can return the results from the query cache, it would actually send that back to the client, and it would be done with at that point. That's the fastest way to get your results if that's possible. So that's why we're going to be talking about the query cache a little bit. If that doesn't work out, it goes to the parser, which parses through the SQL statement, right? Make sure that it's valid. Then it sends it to the optimizer. The optimizer is going to look at it and figure out the best way to execute it. And from there, it actually goes into the kind of the lower level where it gets dealt with from whatever storage engine that your database is running. Okay? Now, of course, with MySQL, you have a lot of different engines you can choose from. The standards of the MySim tables, right? The InnoDB tables, memory tables, some of the newer stuff like Nitro, the SolidDB, the cluster tables, the archive engine, PBXT, and it's very much in alpha, but very promising looking, to be honest, from what I've seen, the Falcon engine. Okay? Just in case you didn't know, InnoDB got bought by Oracle a few months ago. So everybody say boo. Boo. And honestly, even though they have license agreements or whatever, I think MySQL is looking to change their standard default engine. Okay? Now, really, I think Falcon's going to turn out to be a really good thing, but we need to move on. So, we're going to talk about slow query log first. Okay? What's the slow query log? It's going to log queries that take more than a specified amount of time. Okay? By default, it's 10 seconds. You turn this on in your my.cnf configuration file, which is the main configuration file for your MySQL server, right? And when you run a query, and it takes more than, by default, like I said, 10 seconds to go through all this that we just traced out, it gets logged into that file. Now, why is that useful? It's very, go ahead.
Because you want to see what's taking a long time.
Exactly. It's very useful to know where your server is spending all its time. Okay? Now, the resulting log you can look at with the standard Unix commands like cat or tail, or you could use the MySQL specific command of MySQL dump slow, which is an awkward mouthful to say, but it's actually a cool little program. It will give you some results that are meaningful. It'll tell you, I've got a couple of examples down here of some ways that you can do that, but it'll give you some configuration, it'll give you some information about how many times queries being executed and that kind of thing. So take a look at that command if you've never used it before. Here's some sample output from a slow query log, all right? Take a look at this. Of course, down at, first of all, the date and time. It's going to log who submitted the query, right? Where they came from, the host name or IP address. It's going to log the query time itself, which in this case was 20 seconds. The lock time was 0. What does the lock time mean? That's how long it actually holds locks on the table. So this is a very important thing. If your query is locking up your tables for a long period of time, this is really, really bad. So even though that this query might have taken 20 seconds, that might be acceptable if it doesn't tie up your system. Okay? The rows sent 3,979 and it examined 3,979. Now what does that mean? That means that the MySQL server sent back 3,979 rows to the client. Okay? To get those 3,979 rows, it examined exactly 3,979. Okay? And there's the actual command down there. I changed it a little bit, but use whatever database and select your field from the table where the field, another field is equal to some number. Okay? Just real quick before we start on the explain command, the slow query log is a great place to start your query analysis from. You should always have it turned on, to be honest. There's really not any reason not to. So check your servers and make sure that that is configured. Like I said, that is configured in the my.cnf file. Yes?
Just the version of MySQL, everything you're talking about is probably a 5.0 or 5.1 or...
There are going to be some places where I point out some things that are specific to version 5. I don't think I actually cover anything that's 5.1 specific. The slow query log works in 4.1. I think it actually goes back all the way to 3.23. I wouldn't quote me on that. Okay, but it's definitely for some of the older versions. All right. Now, what is the explain command? It is a way that you can take a query and look at how the MySQL server is going to actually execute it. Okay? So this is a really, really cool thing. I call it the query tuner's friend. Okay? It's going to show the execution path chosen by the optimizer for the statement. Now, it's going to show what it would choose just to let you know, and I'm not going to go into this, but if you don't like what it chooses, you can change that. Okay? So you can tell it to do something else. Now, let me show you an explain statement. I've got it in the row format because long way, it's a little too much. So, once again, here's our select statement, and that is, I think, the same one from before. It looks like it. And there's some information down there that we're going to talk about in just a minute, what those mean, the ID, the select type, the table, the type, the possible keys key, all that stuff. We're going to talk about that in just a second. Okay, but that's actually what it looks like. I want to mention real briefly, before I go on into detail about this, there's a tool that builds onto this that I would recommend that you take a look at. If you have a long, complex select statement, that maybe has like sub-selects and unions and all this kind of stuff, this gets really messy. This is a real simple statement. You can see what kind of information it returns. Once your statement gets fairly complex, this gets to be a mess. A gentleman named Baron Schwartz wrote he writes and maintains, I guess I should say, a package called MySQL Toolkit. And it's got some very cool stuff, including one called the Visual Explain command. And it basically takes the explain statement and it formats it really nicely, okay? So let's talk about this output syntax. I've already mentioned basically these are the different fields, so I'm not going to go through that again. But let's jump to this. So what's ID? If you have more than one table that's in your select statement, it will give the tables an IDs. And the interesting thing about this is that it's actually showing you which ones, kind of the order that they go in, okay? The select type is going to be the type of select statement used. The table is going to be the name of the table or the alias of the table. The type, there's different types of joins for the queries, okay? Possible keys are the indexes that MySQL will consider, okay? So they're possibilities. And then keys actually will use. All right? The key length is the length of the indexes is within the key to retrieve results. Rows is the estimated, and I want to emphasize that that's estimated number of rows. It guesses. It's usually pretty good, but it does guess. All right? And additional information is listed under extra. So, breaking this down a little bit, your select types, which is one of those fields. Let me back up if I can. A couple of these, some of these are really obvious. We talked about the ID. The select type is next. The table type is I'll run through the select type here. There's different kinds of select statements. And I know I've got like 3 pages of this. There's a lot of information here, okay? I don't expect you to remember all this in like 2 seconds. I'm going to run through this. These notes are going to be available from my website, okay? So, you might want to take a look at those and download them and use them as a reference. This type of information is also available. MySQL keeps a great set of online documentation at dev.mysql.com. Okay? But the different types of select statements. The simple select, which is a very basic select without unions or subqueries. Okay? An example right there would be a select asterisk from customers where the last name equals. A primary select is the outermost or higher level select. Now what do I mean by that? If your query actually has like a subquery, for example, does everybody know what a subquery is? Okay. We're going to cover some examples that you'll see those, but your query could have multiple select statements, okay? And the primary select statement is the outermost one or the highest level one, if you want to put it that way. If it's a derived select, that's a pretty specialized case. You won't see that very often. The query involves a derived table, including a view, and it's assigned a derived select type. A union select is the second or later select statements in a union. And I gave a quick example down here. You can take a look at that. But you see the union statement down there on the 3rd line of the example, and then there's a select right after that. That select statement would be a type union if you explain this, okay? Now, a dependent union is the second or later select statement in a union that's dependent on an outer query. So, in other words, even though I don't have an example, but if you go back to the one right before that, if that select statement, something in there were dependent upon the outer query, the outer select statement, that first one up at the top line, right? That would be a dependent union, all right? And if that's clear as mud, I'm sorry. That's as good as I can do. Make sure I got everything in order here. You've got a union result, and that's when the optimizer needs to create a temporary table to hold the results of a union. A subquery, which I mentioned, if a query includes a subquery, the first select and the subquery is identified as type subquery. Okay. Here's a good example. See this down here, this example? That's a subquery. You've got a query on the outside where customer or where cm.customer ID is in, and then you've got a subquery. Okay. So a subquery, I already covered that with the dependent subquery. If the subquery relies on information from the outer query. Now I mentioned, I think, a dependent union just a minute ago. Same idea. Your subquery down there depends on something in that outer statement. Okay? And an uncacheable query is a subquery result which can't be cached in. And it's evaluated for each row of the outer query, and that's a really bad thing. Okay? Join types. This was the other part. Now remember, we're talking about the explained syntax, okay? And one of those is called type, right? And there's different types. Those stand for join types. Now, if you thought the last little bit was esoteric, this is even more so. But unfortunately, this stuff is important if you're doing query tuning, okay? I know this is a little complicated, and the first, 300 times you look at it, it's weird. But you do actually get used to it after a while. I'll let you know when I get to that point. But it does happen. All right, so there's different join types. And these, I want to point this out, they are given in order from best to worst, basically. Okay? So when you see these, you want to see a constant join type instead of an all join type, which will be the last one. Okay? A constant, the query is going to have a type of constant value if the constant, or CONST, which stands for constant value. If the optimizer is able to fully use a unique index or primary key to satisfy your search. Now we're going to be talking about indexes in just a minute as soon as we get through this. But a primary or a unique index means that every row in that table for that column is unique. Okay? So a good example, you see like ID fields all the time, and generally they'll be sequential, right? You're not going to have the same ID field, right? So that would typically be like a primary key. The difference between a primary key and a unique key, a primary key field cannot contain null values, okay? Whereas a unique field or a unique index can. That's really the only difference. Because there's only one row, the values from the columns in this row can be regarded as constants by the rest of the optimizer. They're very fast because they're only read once. So this is a really good thing. I'll give a couple of examples there. Select asterisk the table name where the primary key equals 1. Okay? EQ ref or equal ref, reference, whatever you want to call it. One row is read from the table for each combination of rows from the previous tables. I'm not going to go through all this. It's obviously quite a bit. Other than the system and context types, this is the best possible join value. Okay? Skip down to the bottom. In the following example, MySQL can use an equal ref join to process this table. All right, the ref table. The next type is a ref or null. They're going to use a non-unique anywhere from 1 to 8 rows. So it's not really, for example, this is a real good query to show this. Select asterisk from your customer address table, right, where the postal code field is 27713, and I gave it the same one as right here. There may be a lot of customers that live in 27713. Maybe one, but it could be 1,000. Okay, so it could vary anywhere from 1 row to 1,000. If it's a type ref or null, that means that the query is also looking for null values. Okay, so that's kind of a specialized case of that. An index merge. Now, I need to point this out. This is a MySQL 5 or later option. Okay? Now, I'm going to read this and then I'll explain why it is. In this type of join, multiple indexes are going to be used to locate your data. You can only use one index on a table prior to MySQL 5. Okay? Doesn't matter how many indexes you've got on your table, it's only going to choose one of them. Well, after MySQL 5, you can use multiple indexes, and it'll show up as an index merge. A unique subquery is an index lookup function that replaces the subquery completely for better efficiency. This type is going to replace ref for some IN subqueries that follow important. Y'all all just fell asleep, so I'll move along. I almost fell asleep making these things up. I got to be honest, this is some difficult stuff. But I'm going to emphasize once again, you got to understand this stuff to really know what's going on in your queries. Okay? Index subquery. This type of query is going to take advantage of an index to speed up the results on your subquery. It's just like the name says. I'm not going to go through that example. But a range. Everybody know what a range is? When you return a range, it's going to go from one thing to another. Is an example down there between 10 and 20. There's a number of operators you can use that are listed there: equal, less than, greater than, equal to, blah, blah, blah. Okay? An index. This join type is the same as all, which is the last one. Everybody say yay.
Yay.
Okay. Somebody back here is like, yeah, I wish you'd move on. All right. So it's the same as all, except that the index tree is actually scanned instead of the entire table. Okay? It's going to be faster than all because the index file is going to be smaller than the data file. And MySQL can use this join type when the queries use only columns that are part of a single index. And then all, that's when the optimizer is forced to perform a full table scan and read all of the rows in your table to find your results. I gave you a nice little example down there. Take a look at the where clause part of that, where the last name is like percent John percent. It can't use an index on that. You can index last name till the cows come home. That will not use an index. Okay? Yes, sir.
Between 10 and 20, inclusive?
Yes. That would be between 10, 11, 12, 13, all the way up to 20. Okay. Yes, sir.
Anonymous for the tape. I don't think I've ever done this. Can you join between tables of different types? I'm going to assume that you can, but this table is my customers, and this table is addresses, and this is InnoDB, and this is my ISAM.
Oh, sure. No, it will. I'm sorry, I misunderstood.
Are there performance issues when having to join between different table types? Have you noticed anything?
Different table types, different engine types, really, is what you're saying.
Yes.
Are going to give. Some engines are going to give better performance overall than others. So,
but specifically joining between the two, is there?
Well, it's going to depend on the engine.
Okay.
If a table is MySim, it's going to be faster by and large than an InnoDB table. Okay,
Mm-hmm.
but the MySim, of course, has no transactional capabilities whatsoever.
Mm-hmm.
Okay, so yes, the MySim table would have better performance. That would actually improve that query, typically with a read, right? All right. Now that we've gotten through all that, we're going to take a look at some of the things that we need to avoid in queries. Okay. One, a correlated subquery. Now, that's a mouthful. A correlated subquery, another word for that is a dependent subquery. Now, that may ring some bells for you. If it's a dependent subquery, the subquery part is going to depend on the outside part. Okay? This is not a good situation. It will slow up your queries immensely. Correlated subqueries can always be turned into a join statement. Okay? The reason why they give you such poor performance is because they're going to be executed. The subquery is going to be executed once for each matching row in the outer set, and that will bog your system down in a hurry. So how do you determine if a subquery is dependent? Well, does it reference any tables outside of the subquery? If it does, it's a dependent subquery or a correlated subquery. Now, let's talk about some fun stuff, indexing strategies. First of all, you're going to minimally need to use one index per table. That's almost written in stone. I don't want to say it is, but it's really very close. Okay? You don't necessarily want to, in fact, you almost never want to index every column. Why is that? Indexes actually cost. Now, they will, by and large, improve your read performance. However, when you go to write to a table, they take longer to update because it has to write additional information, basically. Okay? So you should, the third part is that you're always going to want to try and use indexes with high selectivity. Now, I'm going to explain what selectivity is and how that relates to indexes, so don't count on that. But it is very important. Now, I already mentioned this just a second ago, but previous to MySQL 5, it's only going to use one index per table in a query. Okay? That does not mean you can have more than one index on a table. I want to specify that. You may use different columns for different queries, right? But it will only use one index from that table in an actual query. I hope that makes sense. One other I want to point out, in the case of OR conditions and a where clause, MySQL will always use a full table scan, so it ignores all the indexes. Okay? Now they have fixed that. It was a fix. It was something that needed to be taken care of anytime after MySQL 5. So let's talk about selectivity. I mentioned that just a minute ago. And that's a very important concept when it's relating to indexing. The selectivity of an index, now I'm going to give you the academic thing here. The ratio of the numbers of distinct values in the index columns to the number of records. What does that mean? Let me show you. First of all, the ideal selectivity is 1. Such a selectivity can only be reached by unique indexes on a not null column, which would be a primary key, or a unique key that's specified as not null, which would be a primary key. So, as an example, we're going to take a look at usernames. We've got an index on the username column, okay? It's in the users table. Now, what this really breaks down to is we want to know, first of all, how many rows are in our table. So we do a count from the table. The second thing we do is we want to know how many distinct usernames there are, and that little query right there will give you that select count distinct username from the users table. Okay? Now, I'm going to throw out a couple of things off the top of my head here. If every row was distinct in your username field, let's say you used a username field of email addresses and they were all distinct. Your query B there would be the same as query A, right? If we had 1,000 rows in our table, in our users table, and we had 1,000 distinct usernames, that would be 1,000 over 1,000, which would be equal to 1. Now, if you remember, the ideal selectivity is 1. That's great. That means every row is distinct. Now, if half of them were the same as the other half, then out of that 1,000-row table, only 500 of them would be distinct, right? So what we would get would be 500 over 1,000, which would be 0.5, 50%. So our selectivity is either 0.5 or 50%, whichever one you want to call it. Okay? Just to back up, when we got the 1, that would be a percent, if you want to look at it that way. I typically would just refer to it as the number, but it will work either way. So, mention again, higher selectivity is better. Okay? If all your index rows were the same, if everybody's username was Fred, there would be no point of having that index there, right? I want to mention this. I've not seen a hard figure for this, but the numbers that I have seen are that the optimizer in MySQL will not use an index if the selectivity on it is around 25 to 30% or less. Okay, so that'd be like 0.25 to 0.3 or less. Okay, it'll just kind of, it won't use it. It'll use a full table scan instead. Because it thinks, and this almost always is right, that that's going to be faster than doing all those lookups. And I'm not going to go mechanics to that. It's an interesting discussion. And one of the resources I will mention at the back is a book called SQL Tuning. He goes into that a lot. They also do it in another book called Database Design and Tuning, which is also on our resource page at the very end of this. Both of those are excellent books, and they go into some of the mechanics of why that's true. Okay, full table scans. I'm not going to spend a whole lot of the time on this because I am running out of time. So we're going to move right along. A full table scan is actually very simple, though. If the optimizer is not going to use any of those indexes, it's going to do a full table scan. It goes through the entire table, reads it into memory, okay, looking for the rows that it needs. Goes through the entire table. That's almost, but not always, that's almost always, let me say that again, that's almost always not the desired result, okay? If your table is really small, it very likely may be faster. All right, that would basically be your exception. How do we determine if MySQL is going to perform a full table scan? We use the explain statement. Okay? When you have questions like that, use the explain statement. I'm going to say that a few times, and you might pick up on that. Okay? There's a list of reasons why full table scans are performed. I'm not going to go into those. Other than briefly mention just a couple of them. There's no where clause. If you do a select asterisk from whatever table, it's going to do a full table scan. Right, that kind of thing. Covering indexes. Now, there are different kinds of indexes. I'm going to mention a couple of them. All right, now, you've got standard ones, and I want to mention these very briefly before we move on. But mention the primary index, the unique index. Those are very similar. You've got a regular index where you just tell it to create an index on a column, right? And that column could have anything in it. The other kind you would have would be a multi-key index where you actually use multiple columns in your index. So if you had two columns, column A and column B, in your table, you would have an index of A, comma, B. And that could be in either order, and that is important. And I'll go into that in just a second. Covering indexes. What are covering indexes? They're an indexing strategy where the index encompasses every field returned by the select statement. Okay? Why is this a good thing? Because it's faster to read everything from the index than use the index to look up the information in the rows. If you remember back to all that mess I went through with the explain, I talked about one of those where it was using something like this. It looked up the information out of the index field instead of looking up the rows. That is faster. Okay, now that may be a weird little concept. You may need to dig into that a little bit. Okay, but your data in those index fields is actually stored in the index. Yes, sir.
Would an example of that be, instead of doing, if you wanted the username and email from a user table, rather than saying select star from users, where the username and the email are in the where clause, if you just said select username, comma, email from users, where username and email are in the where clause. Okay.
Yes. Let me give you another example right here.
Oh, okay.
Sorry. I think what you were saying is absolutely correct. But if you have an index AB on table 1, if you did a select B from table 1 where A equals 5, that would be covered. Okay? Everything in your select statement, the A and the B, are in the index. Okay? So this brings us, where do these covering indexes bring us benefit? There's a few places. I'm not going to go into all these, but if you have large tables, long rows, where the extra columns in the index don't significantly increase, it says key length up here. Anytime you see key, when we're talking about indexes, those are swappable terms. Okay? So as long as it doesn't increase your index length significantly, that type of thing. want to point out one other thing down at the very bottom. The MySim tables do benefit more from this than the InnoDB tables. Because the MySim tables doesn't cache rows, it depends on the OS to do that. Duplicate indexes. Well, duplicate indexes are very simple, actually. And it's just what it sounds like. When a table has multiple indexes defined on the same column, it's going to have duplicate indexes. As an example, these are your indexes defined on some table. You've got a primary key of ID, a unique key on that same column called ID, and another key, just a regular index called ID2, defined on that same column. Okay? These are all duplicates. Why do people do this? I don't really know, but they do. Actually, some of the reasoning, sometimes people don't think they should be doing a select using the primary key as an index, which is, I don't know where that thought came from, but it's absolutely true. So they'll go and make a unique key on the same thing. Now, why this is a bad thing? Because MySQL doesn't look at that and say, oh, these three indexes are all the same. It says, I've got three indexes. And it maintains three separate indexes. When you do an update on that ID field, it has to update it in three different places. Okay? So don't do this. Just use your primary key in this case as your index. You can drop those other two. Okay? Second part to this, I want to point this out real quickly. The duplicate indexes apply to indexes of the same type. It may make sense to have indexes of different types created on the same column. Your indexes of different types. Another is called full text. Okay? You might want to have a B tree and a full text index. That may make sense in certain places. That's you may not want to do that right now, but it is something you can keep in mind. Look at index. So completely is important. I mentioned this. AB is not a duplicate of index BA. Those are actually two different indexes, and they're useful for two different things. Okay? A redundant index is kind of similar to a duplicate index, but they're prefixes of other indexes. In this case, we've got key A. So that's your first index, right? Key AB, that's your second index, and key A10. What that means is it uses the first 10 characters in that column, okay? Why are these redundant? Key A is the first part of key AB is actually key A, okay? MySQL can use that second index to handle the functionality of that first one. I don't know if that makes sense. You may need to think about that a little bit. You could not say key B. That would be something completely different. It goes to the prefix. It can't like take apart the end part of that, the postfix, I guess. All right? And key A10 is just a subset of key A, which is a subset of key AB. Okay? Now think about that for a second, but these aren't necessarily always a bad thing. I will explain. Most often they're not helpful. Okay? Queries that are going to take advantage of redundant indexes, they're also going to be able to make use of the longer index. However, that being said, if wrong, it might be useful to use. And if you think back to the one we were just talking about, A10 might make sense. A was 3,000 characters long. Okay, that would be a lot faster in that case if you could use that index of A10. All right? And there's an example there. I want to point out there's no tools that are currently bundled with the MySQL distribution that's going to let you check schemas for redundant and duplicate indexes. Now, for the sake of time, here it is right here. The next thing we're going to talk about, I'm going to kind of wrap up with this, because this is actually very interesting in my opinion. We're actually going to do this for a little bit. This will kind of help this gel. I'm going to walk through an example. Remember, these slides are going to be available, so don't worry about all this, but what we're doing here is I'm setting up some tables to do some testing on. We're going to create the database up at the top line. And that's misspelled. It's actually used MySQL query optimization. So we're going to use that database. And then we're going to create those tables. There's a table for students, a table for tests, and a table for grades. And here, what did I just do? I hope we just went to the next page. So we're going to insert some data into that. I'm not going to take the time to go through all that, but what you end up with is some values in your student table, 50,000 of them. Some values in your test. There's only 3 in test. And what these are going to tell what our tests are like. Our first 2 tests are worth 100 points, up to 100 points. Our third test is worth 300 points, so it's like the final or whatever. Okay? We're going to drop those into the database down there on the bottom. Now we're going to insert the actual grades. Now, the very first thing I did was a real simple query. What was the average score on the test 1? If you look down, this is the thing I want to point out as we go along. First of all, I did no indexing on this whatsoever. Okay? You'll see in just a minute I put some indexing on it and what effect that has. In this case, it's very fast, 0.06 seconds to go through all those scores. Okay? And it came up with an average of 49.88, which makes sense. They were completely random scores. All right, so out of 1 to 100, of course, it's going to average right in the middle. What student didn't take test 1? There's a query down there, kind of a complex little query. I stopped that query after it ran for 4,200 seconds because it wasn't getting anywhere near done. I don't know how much longer it would have ran. This was on a pretty decent machine. It had 4 gigs of RAM, and it was Xeon chips. So we're not talking about some little toy box either. All right? Just for those who are curious. I did an explain statement on this. I want to point out a couple of things here. It's looking at 2 different tables, S and G, which were aliases. One of these is going to return 50,000 rows, and one's going to return 120, and it actually ends up multiplying those together. Okay? So that's actually how many rows of result that you get, that it's dealing with, and that's why it ends up taking so long. All right? And the last thing is how many students took 0 tests. I canceled that one after 5,700 seconds, so it was a similar situation. Here's the explain on this. It ends up being the same amount of computation. You can see one of them at 50,000 rows, the other at 120. Now, I'm going to alter these tables, and we're going to put some indexes on them. It would have been nice to go into detail about what was in all these tables, but for the sake of brevity, I altered the table on grades, and I added an index on test ID in the first one, and I altered table grades, and I added an index on student ID. Okay? And that took a couple of seconds or whatever. Actually, it took half a second on the first one and just under a second on the second one, so that was basically nothing. If there was a huge amount of data, that would have taken a little bit longer, but I promise you it would have been worth it, because watch this. Now I'm going to rerun it. The first one that hung so long, it was like 4,200 seconds or whatever before I killed it. It now took 1.4 seconds. Okay? That's what an index will do for you in the right place. There's the explain statement. Now, this is interesting. 50,000 rows on the first one, 2 on the second. So it went from 120,000 to 2. That was why you got the big change. How many students took 0 tests? So there's the same, that second one took 1.19 seconds. All right? And it's the same there also, 50,002 rows. Big difference. I have about 5 minutes left, so I'm going to get to go through some of this. real briefly, when you're talking about optimizers for databases, there's two kinds. There's the cost-based optimizer, and there's a rule-based optimizer. Now, MySQL uses a cost-based optimizer. If you'll forgive me for just a second, let me catch up on my notes. All right. And 10 pages later. There's a couple things to point out here. The cost-based optimizer estimates the execution time of performing a query in various ways, okay? And then it tries, and I emphasize that it tries to choose the lowest execution time. Not always right, but it's pretty good most of the time. A rule-based optimizer builds what it thinks is the best query based on a set of rules, okay? That's where, of course, where it gets its name. Rule-based optimizers are going to be quicker to return something than a cost-based optimizer. But cost-based optimizers usually offer better performance in the long run. Why is that? Because there are too many exceptions to the rules, and the calculation overhead of the cost-based optimizer ends up being worthwhile. In other words, the cost-based optimizer, even though it spends more time coming up with that query, the query is going to tend to run faster. Okay? I wanted to point out, they do actually both return correct results. One just might run a little faster than the other, okay? And the cost-based optimizer is going to use index selectivity, there's that word again, to determine the best execution for joins, okay? If you're serious about query tuning, you need to look into your index selectivity. If you don't understand that, that is something you do need to understand, okay? It's going to make wrong choices, I mentioned that. That's why explain is your friend, right? So we'll all have that down. Schema guidelines. Real briefly, I probably wrestle with this with my developers more than anything else. As you're developing code, it's real easy just to kind of make something big. If it doesn't need to be, don't. That stuff takes up space and makes your stuff run longer, basically. All right? If the smaller your data type, the more index and data records can fit into a single block of memory, and the faster it ends up being. Okay? The other thing I want to point out, I don't want to get into this whole debate, but normalize your data first and then denormalize it later. All right? Don't do that backwards, shall we say. All right, the query cache is kind of a weird little beast. It can be very, very good, but it's also kind of difficult to tune, to be honest with you. You can look at a system that's running, and you can make it bigger, which you would think would make it better. Doesn't necessarily mean so, okay? Which that's the second bullet point there. The bigger query cache does not automatically mean better performance. Why that is, I don't know. I really can't explain that. Just know that that's true. And test. The last thing we're going to be talking about is benchmarking. All right? I love to benchmark. I really do. It's probably the thing I like the most about my job, to be honest. When you perform benchmarks, does everybody know what benchmarking is? If I'm benchmarking something, I'm kind of testing it out in a controlled environment. And then I'm going to go and make changes to it and see what happens. Okay? When I'm performing those benchmarks, you want to change one thing at a time. If you're changing something in the configuration of your my.cnf file, okay, the amount of memory you've got allocated to something or something like that, only change one thing at a time. If you change two, you'll never know which one gave you the good result. They may both have, but one of them may have done really well and the other might have actually slowed things down. So it was dragging. You see what I'm saying? If you change one thing at a time, you take care of that problem. That stuff like the configuration of variables, the addition of an index, the modifications to your schema table, that kind of thing changes to your SQL scripts, okay? Rerun the benchmarks after making a change, that's fairly obvious. And the last thing I want to point out about this is when you make comparisons, make them apple to apple and not apple to oranges. And what I mean by that, this burns me up. I wrote on my blog not too long ago about a test I read about where they were comparing Postgres to Oracle. Now, I don't have a dog in either one of those hunts, so I can be an objective bystander about this, all right? Because we weren't comparing MySQL to Oracle or anything like that, right? You read through the test, and it said, basically, it said Postgres ran a little bit slower than Oracle. Okay, but then you look into it, the Oracle database was running on one set of hardware that was different than the Postgres hardware. I don't even know which was better. It doesn't matter, they were different. If you're too lazy, if you don't have enough money to go out and buy 2 sets of equipment to do that kind of test, right, the same thing for both, then take the time to redo it on the same hardware, all right? Don't be lazy, please. Oh, burns me up, as you can tell.
Tell us how you really feel about it.
Yeah, I'll try and hold back on that. I'm not going to go into this very much, but when you're doing benchmarking, it's really best to have something that's basically set up just for benchmarking. Okay. Now I'm fortunate in that here we have that, but that's not always the case. If you're having to run it on something that's not like that, you're going to want to turn everything off that you can. Okay. Network traffic analyzers, you know, non-essential daemons, the mail programs, and that kind of stuff. And I do point out that you probably want to turn off the MySQL query cache, because if you're running select statements against your database, it's going to store those results, right? So it will give you invalid data there, basically, most of the time. All right, I'm going to skip for just a second to this one. I want to point out a couple of things here as we finish up. Some of the tools that you may want to look into down the road, SysBench, SuperSmac, the Apache Bench program, and some of the frameworks that have been built up are the JUnit, and some of you Java people might, I don't know, something in Java. I'm not a Java person, sorry. I've offended the Java gods, I'm sorry.
You will be.
I did stop at Starbucks on the way here, and I got some Java, so I don't know. But MyBench, which is a program I've used, I'm going to talk about that just a little bit more. That's in Perl. And a program called the Winch. Not really sure what they mean by that, but that's in PHP. Okay. The last one is the QPP, the query processing programs. We're developing those here in-house. I'm rather proud of them. I wish I could say I had more of a hand in writing them, but there's various parts to this, and I'm not going to go into this, but we've got like a sniffer that you can use to gather your data from your production data going through your network. Think of it as a network sniffer just for MySQL. Okay. It has what we call the query bench part of it, that you use that data to run against your test server. And we're also writing a query parser, which will take that data and look through it and say, oh, this query gets run umpteen thousand times. Okay? This query only gets run once, but it's taking 30 hours to run. Okay? There's nothing, in my opinion, and I'm going to say this as fact, there's no complete test set for MySQL currently, and this is not finished, okay? But the MyBench program, which we actually used part of that, he has a Perl module in there. Jeremy Sawadney is the one who wrote that. We use a module out of that for some of this. And for example, it's kind of a nice little program, but you can basically program it to run like one query against your database, which really isn't indicative of your real production data, right? So we're working on that, and my time is up. There's the resources. I mentioned SQL tuning, MySQL database design and tuning. There's some websites. I want to point out in particular the MySQLPerformanceBlog.com. Okay, those guys are really smart. If you want to read some benchmarking information about MySQL, go to that site. It's some great stuff. PlanetMySQL.org. If you are interested in MySQL, that should be one of your websites, and I would actually recommend you plug it into your whatever reader you're using for blogs, because basically what it is a list of blogs from different people, and it all gets fed into like an aggregate blog, okay? Mailing list, I would point out the general mailing list for MySQL, which is at list.mysql.com. You can sign up there. There's quite a bit of information that goes through there about SQL tuning. That actually is it, and I just wanted to say thanks to everybody. I really honestly enjoy this. I hope you see that. But I hope also that this has been really helpful for you.